Welcome to aminacademy.com. In fluid mechanics, let us discuss about flow through Borda's mouthpiece. A short cylindrical tube attached to an orifice is such a way that the tube project inwards to a tank is called an internal mouthpiece. This is called an internal mouthpiece. It is also called re-entrant or Borda's mouthpiece. If the length of the tube is equal to the diameter, the jet of liquid comes out from mouthpiece without touching the wall. That means that jet is not touching the wall of the tube. This type of mouthpiece is called running free mouthpieces. But if the length of the tube is about 3 times its diameter, the jet comes out with a diameter equal to the diameter of the mouthpiece. That means here this length is more. Means suppose if you put length little more, this is called running full of mouthpiece. Now we'll consider both cases one by one. First, Borda's mouthpiece. Borda's mouthpiece running free. Let H height of liquid above the mouthpiece. That here the H is here. Then A is area of mouthpiece. AC area of contracted area at vena contracta. VC velocity at velocity through the mouthpiece. AC equal area of contracted jet. Area at contracted jet you can write. Jet in the mouthpiece. Jet in. Now pressure force on entrance. Here pressure force on entrance is equal to rho g, density of water, g gravity, and A and H. Here H is the distance of CG through A, area of A from free surface. That is, so we can equal this one rho g A h here, h equal to h. Now this is first one. Now according to Newton's second law of motion, that is force equal to mass into acceleration, second law of motion, the net force is the rate of change of momentum. Net force is a rate of change of momentum. Regarding this, we can write now mass we will calculate. Now mass of the liquid flowing per second, mass per second flowing is rho into AC into VC. Now therefore momentum, rate of change of momentum equal mass into initial final velocity minus initial velocity, Vc minus 0, because final velocity is 0, which is equal rho AC V square. Here we can write this as rho AC V square. Here Vc equal to V. Now equating 1 and 2, rho A, rho G A H, rho AC Vc square. You can write Vc itself here, not necessary, directly you can use it. Then from I keep this one is 3. Applying Bernoulli's equation, applying Bernoulli's equation for to free surface of liquid and section 1 equation at free surface and section 1 here free surface, and from free surface and section 1 we are calculating, that is P over rho G plus V squared by 2G plus Z equal P1 by rho G plus V1 squared by 2G plus Z1. Now at center line of mouthpiece, the datum is therefore Z equal H, Z1 equal to 0, and P by rho G equal P1 by rho G equal to P atmosphere equal to 0. Therefore, we can say V1 equal to Vc and V equals 0. Therefore, we can apply in all the values in Bernoulli's equation. 0 plus 0 plus h equals 0 plus Vc squared by 2g plus 0, or directly can write h equal Vc squared by 2g. Therefore, Vc equal 2gh under the square root. Substituting this Vc in 3. Substituting in 3, we have the equation 3 is like rho GAH equal rho AC VC square. Therefore, rho G A H equal rho AC 2G VC square equal to 2GH. So, both here rho cat. So, then A equal 2 AC. A equal to AC because H also cut G cut. Therefore, A equal to AC. Therefore, coefficient of contraction equal CC equal AC by A, which is equal 0.5 because 1 by 2. 1 by 2 equals 0.5. Since there is no loss of head, since there is no loss of head because it's running full head, loss of head, therefore coefficient of velocity equal 1, we can keep it because it's full, no loss. Therefore discharge through re-entrant mouthpiece when running full is Q equal CD A root of 2GH, which is equal here 0.5. Therefore coefficient of discharge here now CD equal CC and CV. CC into CV equal 0.5 into 1 equal 0.5. So that CD is 0.5 A root of 2GH. This is a discharge of Borda's mouthpiece when running full. Now the second case, Borda's mouthpiece running free. Now Borda's mouthpiece running full. Before we did Borda's mouthpiece running free, now here running full. Now the same The previous things, h is height of liquid about atmospheric, v1 is velocity at outlet, area of mouthpiece, ac is area of flow at vena contractor, cc, vc is velocity of liquid at vena contractor as above. Here head loss, hl we can write vc minus v1 whole squared by 2g, because we are keeping the same as before, like h, v1, a, ac, vc. Now continuity equation, that is ac bc equal a1 v1. Therefore vc equal a1 ac v1, which is equal v1 over ac by a1, that is v1 by ac by a1 is cc, which is equal v1 by 0.5. Therefore vc equal to v1. Substituting these values in hl, therefore hl you can write vc is 2v1 minus v1 the whole square by 2g. That is equal v1 squared by 2g. Now applying Bernoulli's, equation in water free surface and free surface and section 1 will get P by rho g plus v squared by 2g plus vz equal p1 by rho g v1 squared by 2g plus z1 plus head loss. Now taking datum is 0, therefore p by free surface p by rho g is 0, velocity also 0, then datum is h equal, this side is p1 by rho g 0, that v1 squared by 2g, z1 is 0, then head loss. v1 squared by 0 plus head loss is v1 squared by 2g. So h equal 2 v1 squared by 2g, cut both, therefore v1 equal root of gh. Here v1 is actual velocity as losses have been taken into consideration, therefore but theoretical velocity is equal root of 2gh, therefore the coefficient of velocity is cv equal c1 v1 by vc. v1 by vc is gh over square root of 2GH, which is equal 0.707. So 0.077. Next, as the area of the jet at outlet is equal to the area of the mouthpiece, therefore we can write CD equal CC into CV. Here CC is 1 because running full, CC is 1 and 0.707 equal 0.707. Therefore discharge through Borda's mouthpiece when running full is equal CD into A 2GH equal 0.707 A to root of 2GH. Therefore, this is the discharge Q when running full. Here, when running free, discharge is 0.5 A root of 2GH. Running full, it is 0.707 A root of 2GH. We have done. Please subscribe our YouTube channel.